Okay. Grammatical format. Today, in the last class, we saw that for any context-free language, you can write context-free grammar. That grammar is composed of production rules, and the rules are individually, each rule. So this grammar must have at least one start production rule. How we know that this is start production rule? It has capital S on the left side. It may have more than one start production rule, but minimum one start production rule must be there. Otherwise, you always start working from that production rule. Exactly like you have a start state in FATG. So you always start working from the start state. Each production rule is composed of two things, either terminal or non-terminal. Until you have a single non-terminal in your sentence, we can say that the production is not finished. The final thing should have only terminals. There should be no non-terminals in the final sentence. So then we can say that production of the sentence will be completed. Terminals are all small case letters, all signs, symbols, mathematical operators, all notations. Anything which is not replaceable is terminal. Another thing is you will never see terminal on the left side of your production rule. Non-terminals are always be in capital letter. It can be on the right side or the right side, but for sure all non-terminals must appear on the left side also. So because they have to be replaced by something. So if it is on the left side of the production rule, so then you can say that okay, this non-terminal can be replaced by this thing. Non-terminal can be replaced by either terminal or non-terminal or combination of terminal and non-terminal. So this is what we saw last time. Now we are saying that all regular language, but you remember that we saw last time that when you have a grammar, so it has ambiguous grammar, and ambiguous grammar means that any grammar by which it is possible to generate a word more than one way. It should have more than one parsing tree. So then this is not good. Machine will be confused that which method it should use. So we want to clean the grammar. So we did not learn anything how we clean it. So now we will see in this chapter how we clean the grammar. Okay. So all regular languages can be generated by context-free grammar. So context-free grammar has a big scope. You saw in last chapter. It can represent regular and non-regular languages, but specifically, if we talk about regular languages, we can say that all regular languages must be generated by context-free grammar. Okay, and so can some non-regular languages, but not all possible languages. So what does it mean that when you have a context free grammar, it can represent regular languages, it can represent non-regular languages, it can represent context-free language, but still there are some languages which have a bigger scope than all these three languages. They cannot be represent those languages. So if I can draw something like this, let's say this is a regular language, this is a and then non-regular languages, and then this is your context free grammar, let's say, and then there are some other languages. So it is something like that. So its scope is like this. Okay. So for a given context free grammar, so now there is a more terminology we call a semi word. What is semi word? We need to understand this. So semi word is a string of terminals, maybe none, maybe no terminal, with exactly one non-terminal on the right side. In general, a semi-word has a shape. So when you have something like this, you may have more than one terminals, but the non-terminal should always be one and always be at the right side. That's it. So then we say this is a semi-word. Okay. Or you may have one terminal and one non-terminal. Still it is good. Or you may have no terminal, just non-terminal. Still it is good. So semi-word is a string of terminals, maybe none. Look at this. Maybe none, no terminal, concatenated with exactly one non-terminal on the right side. In general, semi-word has a shape like this. So this is the format of your semi-word. Okay. So all these are valid semi-word. Why we call semi-word? Because until unless you have a non-terminal, it is not a word. So word definition is without any non-terminal. So we call this a semi-word, but it has a condition that non-terminal should be always be only one and on the right side of the word. All regular languages are context-free languages. We already know that because context-free languages have a bigger scope. So the regular languages have a less scope than the context-free languages. Context regular languages are subset of context-free language. So that's why all regular languages are context-free also. So we show that for any FA, there is a context-free grammar such that the language generated by the grammar is the same as the language accepted by the FA. So what we are saying that if you have an FA, so you can convert your FA into context-free grammar. So if you have a context-free grammar, and if that context-free grammar represent a regular language, you can convert that context-free grammar into FA. So it is both interconvertible. So now today we will see how we do that. So the alphabet summation of terminals is the alphabet of the FA. So these are some guidelines how we do that. So non-terminals are the state names. So when you have a non-terminal, so these are the state names. So if you have grammar, so this is a state name of your FA. This is the label of your that state, and this will tell you that you have a connection from X to Y. So direction is X to Y. So that's the idea behind that. And if you have something like this, so it means that there is a self loop here. So for every final state, create a production. So whenever you have a final state, you need to create a production rule. X tends to lambda. So it means that this is a, if you have any non-terminal which is representing this production rule, it means that this non-terminal must have a final state. Okay, so that's the idea behind that. So we will see one example that then you can better understand how we convert that. But these are all possible scenarios which you need to take care. So every word accepted by FA can be generated from the context-free grammar, and every word generated by context-free grammar is accepted by FA. So it means that context-free and generates exactly the language accepted by the original FA. Okay, so let's see this example here. This is not a complete FA, but it is just an example. It's not necessary that you can convert FA. You can convert TG also into FA. So now, if you have something like this, let's say this is FA, partial FA. It has missing something. So how you convert the grammar from FA? So we know that all the state names are the non-terminals, and so X x2, so we can say this is x1, and the going to x2, it means direction is this, and the label is a, so ax2. So this is the way you can write this. Okay. So the exactly same way you can write, look at this one, x2 b x3, x3 a x4. This is the way you can write this. And now if you have this FA here, first of all, let us check that this is a valid FA or not. So it has states, it has a start state, it has A, B, A, B, A, B. It is taking care of garbage collection. So this is valid FA. So now our job is to convert this FA into context-free grammar. So first we pick one state, this state. So we are saying, okay, S can be replaced by, so now look at this one, B and it going back to S. So B and S. So then we can say S can be replaced by outgoing edges only. This one, A, and where it is going toward M. So we cover all outgoing edges of this state. So now we pick this state and cover all outgoing edges. M can be replaced by AS. M can be replaced by this thing, AF. Now we covered all possible outgoing edges of this. So now we take this state. F can be replaced by AF. F can be replaced by BF. And this is a final state. So then it should have this lambda also. So this means that this is a final state. It has a final state. If you have more than one final state, so that state must also have this production rule that it can also accept lambda. So any question here? If you guys have any question here. All good. It's not hard, huh? So now this is a way, so you can do this, and you know that if you have this grammar exactly, you see whatever I write here, it is written here. So I clean this. Let me clean this because it is already written here. We can, in short, write this also in this way. We can say that S can be replaced by AM or BS. So it is two production rules. Both have the same start production rule. So then I combine that, but still it is two production rules. Or then we can say M can be replaced by AF or BS. And then we can say F can be replaced by F can be replaced by AF, BF, lambda. So still it is 1, 2, 3, 4, 5, 6, 7 production rules, but because they are replacing the same non-terminal, so instead of writing two individual production rules for S and two individual production rule for M and three individual production rule for F, we combine them and we write in short. It does not change the meaning of the grammar or the behavior of the grammar. It's just a different writing style. That's it. So this is also same thing. So now we can convert our context-free grammar into production rule. And just imagine that if you have this grammar, you can draw this grammar into the FA. You can convert this grammar into FA. So it's vice versa. So now we can see that the we have a word. This word is this one, BAB, and how we can parse this word in this production in this FA. So if you have that word, so I just show here that what is the path you choose and how you go here, and you can finish this word. And you see that once you finish the last letter A, you are at the final state. And then we can see that is it possible that we can accept this word by the derivation method from this grammar. So look at this one. So we start from BS and then we replace S by AM, and then we did this because we have this word in front of us that we want to generate this word, and we choose different production rules and we generate a word. So this is what does it mean that if you have a regular grammar, if you have a context-free language, and this language represents regular language, so its FA or its grammar both can generate the same word. It is not possible that you can generate a word, you can accept a word from FA, but it is not accepted, or you are not able to derive that word by the grammar of that respective FA. So it is not possible. So both can be helpful, and you can find the solution by both means. Okay. Now we are saying that we have this another example. Again, we just convert this into grammar. So look at this one. It is almost the same thing. AM, AM, and BS, and then BM, AF, and then BF, AM, and then F has a lambda. So this is a lambda. So because of the final state. So we convert this FA into the grammar. Any question, guys? So far, are we good? Okay. So now, whatever I just explained you is a more formal definition of that. A semi-word is a sequence of terminals, possibly none, followed by exactly one non-terminal. We already saw this, the definition. The language generated by CFG is regular if all of its productions have. Okay, now we are saying, this is a new thing, that how you know that by looking at the grammar, that this grammar represent a regular language. So you have two, three different grammars. How you know that this grammar represent the regular language? If you have a grammar and all of its production rules are in this format, either you have a semi-word, non-terminal, or semi-word means something like this, or just word. If all of your production rules are like, it can have lambda. All of your production rules are like this. Either you have a semi word or just word or lambda. Then, and you do not have any production rule which has non-terminal somewhere in between, or start with non-terminal, or just non-terminals, more than one non-terminal, or more than one non-terminal here, or something more than one non-terminal here. So if you do not have any of this scenario, then we can say that the grammar represents a regular language. Okay, so this is basically, so the language generated by CFG is regular if all of its productions have the form, that whether it is semi-word, all the production rules are semi-word, or just word. Okay. Now we can see this by constructive algorithm. So let's say we have a grammar, and if you see this, this is your non-terminal, this is your word, and this is exactly non-terminal. Word exactly non-terminal, word exactly non-terminal, or just a word, just a word. So this context-free grammar represent regular language. Okay. So now where n are the non-terminals, w's are the strings of the terminals, and the parts are the semi. Yes. So one state for each non-terminal state name as a start state, we can add final state. So we can add a final state when we see that if there is a non-terminal which can represent lambda, so that non-terminal will be the state. So that state will be the final state. Okay. So this is what we are saying here. So now let's see here. Any path in this TG. So now you can write a grammar, convert a TG also into a grammar. From start state to the final states corresponds to a word in the language of the TG by concatenating labels, and simultaneously corresponds to a sequence of productions in the context-free grammar generating the same word. So every production of a word in this CFG corresponds to the path in this TG from star to the plus. Therefore, the language of this TG is exactly the same. So basically, it says that if you have a TG, you can also convert that TG into the grammar, because if you notice here, this is not an FA, because FA will never have a, because what does it mean if you have something like this? Let's say I give you an example. Let's say we have a state. We can say this state is A, and it's no, we can write a production rule A and then small a, three small a's, and then capital B. So what does it mean? It means you have one state, it is A, you have another state which is B, and its label is towards A to B, and its label is three A's. This is not FA, because FA never have a word on the label. This is TG. So it means that this all represent TG. Huh? You might have a single, if your word is just a letter, so then it is FA. But if your word is more than letter, so then it represents TG. Okay, and this it says here that you can convert TG into grammar into TG, and they represent the same language, and it is a regular language. Okay, this is what does it says here. Look at this one. So we have this production rule, this grammar, and this grammar has three production rules. And all these three production rules are start production rule, and we can say that it represents a regular language, because if you see the first production rule, this is a semi word because it has all terminals and only one non-terminal at end. This is a semi word because terminals and only one non-terminal at end. This is semi word because just a lambda. Lambda is also semi word, or just if you have just non-terminal terminals, that will also be a semi word. So now, can we convert this into the TG? So let's start. We have S, and then it says AAS. So self loop AAS. Then BBS. So then another loop BBS, and then lambda. It means that either you can put here start state a plus sign, or if you don't want to do this, so same thing, you can say lambda and the plus. So without doing anything, you can go to the lambda. It is the same thing. So we just draw TG from, so this is not FA, this is TG, because it is passing the word toward the edges. What is the regular expression of this? AA or BB star, because you can have star will give you lambda, or if you have AA or BB and this is a loop, so star will give you any combination of that. This is a regular expression of that. So now we are saying that alternative of this is where WQ is not lambda, so might be you have a word here and it goes there, so it is also possible. So you can do that also. If you have more than one final state, so this is also, you can have a word also there inside of the lambda, because lambda is also a word actually. If you see that this is a word without any letter, it's the same thing. Okay, so now look at this. We have this grammar here, and this is context free grammar. We will see how many. We will see 1, 2, 3, 4, 5, 6, 7, 8, 9 production rules. How many terminals it has? S, X, two terminals. Oh, sorry, non-terminals. How many non-terminal it has? Two non-terminals. How many terminal it has? A, B, and that's it. And how many start production rule it has? 1, 2, 3, 4, 5. So 5 start production rules. All those production rules which have stats, which have S here, are the start production rules. Okay. And is this grammar represent a regular language? How we check that? If all production rules have a semi word, this is a semi word. Non-terminal, one exactly one non-terminal and at end. One non-terminal, semi word, semi word, semi word, semi word, semi word. Yes, all these are semi word. So this grammar represent a regular language. Now, are we able to draw this grammar into its respective mathematical model, and what that mathematical model will be? For sure, it is not FA, because you have 2A here, 2B here. FA does not accept a word. FA only take care of letter by letter. This is TG. So we are saying we start from the start state, which is S, and then we take care of this AAS, BBS, and then we have another state X, ABX, and then uh, we take care of this AA, and then ABX, BAX, S can be lambda, so we draw another final state here, and this is lambda, okay? And then we are saying that X, we have X, AAX, BBX, AB, from this side to S, ABS and BAS. Look at this one. We completely draw all the possible production rules, and this will give us this machine, and this is proper valid TG, and this FA, this TG is convertible into grammar, context-free grammar, which represents a regular language, and we have this grammar can be converted into TG, which represents a regular language, interconvertible, and they both represent the same machine. Their if you have a regular expression, that regular expression will represent both machines. It is the same thing. So that any question here, now we are going to change the topic. So guys, are you there? So Nikhil, is it everything is good?
Yeah, everything's good.
Quinton, are you happy with this? Okay. James Evans, are we good?
Yeah, it makes sense to me.
Very nice. So now what we will discuss, this is very important, and you will see that your assignment, which I already published, is have a lot of questions from this part, and you will see this part major contribution in your final exam also. So we will see I will what we are covering now. So you will see at least what I guess that 20 or 25 point question in exam. Okay. In your final exam. So now we are saying that we saw this lambda is not good. Lambda always create a problem. It is not terminal, it is not non-terminal, and it does not satisfies the definition of both things. So is it possible that you have a grammar and it does not have any production rule which is like this? And if you have a grammar, it has any production rule which generates lambda, we will say that this is a lambda production. It's an empty word. This is called a lambda production. Okay. So if the empty word is in the language, a production of this kind is called a lambda production. That your language is producing a lambda production. Okay. So is it possible? So this is one language. It is, so is this language produce a lambda production? Yes. Which production rule? X can be replaced by this one. This is a lambda production rule. Is there a possibility that we do not have this lambda production rule, but we have a language which can accept everything else lambda? Yes. If you have a context-free grammar and that context-free grammar has a lambda production, there must exist another context-free grammar which represents the same language, which define the same language, but other than the lambda productions. So you need to find that how we remove or how we kill all these lambda productions. We are so frustrated with the lambda, we will not use the light word. We will say kill the lambda production, kill it. I mean, we are tired with that, this lambda. So we want to kill the lambda production. So what this thing says, it says that if you have a language L and it is represented by a context-free grammar and it has a lambda production like this, okay, so then there must exist a different context-free grammar which has no lambda productions, but both languages can represent the same language other than lambda. So it will not accept lambda, but all it will accept every other word what it will accept. Okay, so this is basically what we are saying. Now our job is to find that alternate context-free grammar. If your grammar has a lambda production, how we find the alternate context-free grammar which represents the same language but no lambda production? In this case, what we will do, so let's look at this one. We need to see our job is killing lambda productions. So delete all lambda productions. This is what we want to do. So we will see that if you have a lambda production in your grammar, having that production rule, what are the possible words you can generate in presence of that lambda production rule? So now you need to add those words or some extra production rules in your grammar. So you will not miss any other word which is possible to generate in presence of lambda production rule, and it is not possible now that you cannot generate that in absence of lambda production rule. You can, so now what we are saying in short again, we will see if you have a lambda production. Let's see this one, this grammar. It has a lambda production. Okay. So now we will see that what are the other production rules are possible with this. Look at this one. X can be replaced by, okay, I can show you. S can be replaced by XB. This is one production rule. Okay. Oh, sorry, I write other way. X and small b. And X can be replaced by lambda. So now if you replace X with lambda, it means you are able to produce S can be replaced by B. Now, if you delete this production rule, you need to add this production rule in your grammar that you do not miss any word which was possible to create or generate or derive in presence of this production rule, and now it is not possible because you do not have lambda there. So if you do not have lambda there, you are not able to generate this S can be replaced by B. So now we need to add that here. Okay, this is something we want to check that so we can get a compatible production grammar which will be equal to this grammar, but it will not have this lambda production. Now we are trying to clean our grammar. Okay, so what we will do, so we will see every non-terminal and see its impact directly or indirectly by the lambda production rule. Okay, so let's say we pick first X non. So how we know that this, okay, first of all, is this, so I have a question with, let me ask this question to who should I ask this question? Let's say Nikhil. Nikhil, can you tell us that this grammar represents uh, regular language?
Um, I don't think it does.
Why?
The AYA is the only reason that throws me off, but
That's the only reason?
um,
Okay, first of all, your answer is right. And the reason you pick also right. But this is not right that this is the only reason.
okay.
Okay, why AYA is the reason? What is wrong here?
Because it has like a non-terminal, then a terminal, then a non-terminal.
Okay, and how it should be?
It should be that it has like only the uh non-terminals and then the terminal, or vice
Uh,
versa.
I mean, other one, just terminals and then not. So why should be at end? So it should, if it is, if, oh man, if it will be something like this, then you think this is good?
I think so.
Or you are saying this way?
Both of those would be accurate, right?
No.
Is it just the first one?
Yes. And what is this first one?
That would be non-terminal.
But what do we call that?
Semi-word.
Semi word. This is not a semi word. Look at this one. From where we start. The template of the semi word. Only all terminals first come and then only one non-terminal. That's it. Okay. So this is semi-word, and word should not be non-terminal should not be in between. So this is not a semi-word. This is also not a semi-word because you have non-terminal in the start. It can have one non-terminal and one terminal, but X should be after B. This is right. This is semi-word because just terminals are also can be there. Oh no, sorry. This is, oh yes, yeah. This is right. This is right, but this is not a semi word. But if but if your production rules are just composed of a word, this is also good for the regular language. So this is semi word, no non-terminal. This is semi word. This is good. This is good. So only these two production rules are not good. So this grammar does not represent the regular language. Okay. This is for sure. Now we have this production rule. We pick one production rule, let's say X, look at this one, and it can be replaced by Y. We pick this production rule, and we want to see that what happens if you replace, can you replace Y with lambda? No, you cannot replace Y with lambda because Y can be replaced by either B or X. So it means that lambda has no direct or indirect uh, effect on this production rule. So this will, if you have this one, it will not give you any new nothing. You don't need anything if you have this. If lambda is there, it will not affect this production rule. This is what we are saying. Okay. It produce no new formed by the rule. Production newly formed by the rule, so it will not, you don't get any new production rule. If you have this production rule, S can be lambda, and it is not there, so it has also no effect. So you will not be get any new production rule. Now we check y x with all possible production rules because x is only two production rules. Now we check y non-terminal. Y can be replaced by B. This is just B. It has no non-terminal with that. So even we do not need to write that here because it does not make sense because terminals will never be replaced by anything. So this is good. Y can be replaced by X. So Y can be replaced by X. So X also does not have anything with beside that. So it is also not generate any, not give you any new production rule. So now we check these two production rules. Now we check S. So this is just non-terminal. We don't need to check that. We need to check these two. So now if you have S can be replaced by XB, and here you see that X can be replaced by lambda. So if you replace this X with lambda, you can generate a word S can be replaced by B. So you need, so it means that when lambda production rule is there, you can generate this word B from this lambda there. So now if you remove this lambda from the grammar, you will no more be able to generate this word. So then you need to add explicitly this new production rule. And then, so we write that if you have this production rule, you need to add this new production rule here. And then let's see another production rule. S can be replaced by A by A. So now look at this one. When you have S can be replaced by A, Y can be replaced by X by this production rule. And X can be replaced by lambda by this production rule. And finally, it will be A. So it means that indirectly, if you have Y here, Y can be replaced by X, X can be replaced by lambda, lambda can be vanished when you concatenate with the word. So you will have A here. So it means that this will generate, it is possible that when you have this production rule, you can generate this word. So you need to add this word. It will not be possible if you delete this lambda production. So then it will not be, you are not able to generate this double A. Okay. So now what we are saying, for okay, we need to delete this production rule. So you see, we do not have this here, no production rule. Write all remaining production rules as it is, other than X can be replaced by lambda. So Y can be replaced by BX, it is here. X can be replaced by Y, it is here. S can be replaced by A is here. XB is here. AY is here. Now you do not have this lambda production here, you delete that. So in absence of that, in presence of that, you can generate two words B and AA. Look at this one, B and AA. And how you can get that? By replacing S. So on S, you can write another word B and or AA. So by adding these two production rules, now you have a new grammar which is equal to this grammar which is already there. So now these both grammars, this grammar and this grammar, are equal to each other. They define the same language. Only one difference, it has no lambda production, whereas it has lambda production. they are equivalent to each other. Are we good? So guys, any question in this? Do you understand? Okay. So silence means yes, that you understand this thing. Okay, if you're happy with this, so let's move to the next topic. So this is called killing lambda productions. Whenever you have a grammar, this will be the first step. You always kill the lambda production. Okay. Now let's go to the next step. So the next thing is unit production. So how you kill the unit production? A production of the form where you have a non-terminal and it can be replaced by one non-terminal is called a unit production. So you have A, it can be replaced by B. This is a unit production. So one non-terminal can be replaced by exactly one non-terminal. So X can be replaced by Y. This is a unit production. So these kind of productions are called unit production, exactly one non-terminal. Okay. So now if you see this in this grammar, in the previous grammar, this is unit production. This one and this one is unit production. Okay. So these are the unit productions. So now we are saying that if you let L be a language and it can be generated by this context-free grammar, and we assume that we done the first step, no lambda productions, then there must exist another context-free grammar without lambda productions and without unit productions. Okay, so what we are saying, if you have a language, this language is represented by context-free grammar, and this grammar has no lambda productions. You already done the first cleaning step, but it has a unit productions. So there must exist a new grammar which definitely have no lambda productions and also no unit productions. So you have a clean grammar now. Unit production is not doing anything other than increasing the resources, computational cost. It's not beneficial. So it is not doing anything. So now this is what I just explained to you is written here. So we have let L be a language generated by CFG, then there exists another CFG that generate all the words of L except lambda such that all the productions are of the form sequence of non-terminals and exactly one terminal. So this is, and then you can convert that into the unit productions. Okay, so now how we see how we kill the unit productions. So I think that when I show you the example of this, then you will be in better position to understand this. So I want to skip this slide and go to the next slide where we see the example, and then I will come back here. Okay, so look at this one. So this is our grammar. First of all, this grammar, I have a question with you guys. Who will give me the answer? There's some question here. Okay, question to say yes. Jacob Morris, are you there?
I'm here.
So is this grammar which I just show you has any lambda productions?
It doesn't look like it.
Okay. Does it has unit productions?
Yes.
How many unit productions it has?
3.
3. Does this grammar represent regular language?
Yes.
Perfect. So because all are semi words. So now this is good. I'm very happy that you guys understand this. Okay. So now again, what we will do, we will separate from this grammar all those production rules which are unit productions. Okay. So we are saying from this grammar, as just James mentioned us, that it has 3 production rules. So we separate those production rules. We said, okay, these are the production rules and these production rules are good. They have no problem. They are decent folks. Okay. So now we want to see that what is the direct or indirect impact of these unit production rules in your grammar, what does it mean? If you have these unit productions, what are the possible words you can generate directly or indirectly by these production rules? So then what you need to do, what exactly the same idea, you add those words by adding those production rules in the grammar and delete these unit productions. So then you will not miss anything in absence of that. Okay, that's the same idea what we have before. So now we pick one by one production rule and check directly, indirectly. So we say, okay, let's pick this production rule. S can be replaced by A. Okay, S can be replaced by A. So now A can be replaced by B. Does not make any sense if small b is a terminal. So this is a word. So A can be replaced by B and small b, and it means that if you have this production rule, S can be replaced by A. So A can be replaced by small b. So S can be replaced by B. So this is a one production rule. This is one word which you can get, but it will be not possible if you delete this unit production. So now it means that this production rule gives us this new additional production rule. Okay, so this gives us this one. Very nice. Now we will see what is its impact indirectly. So S can be replaced by, so we go here. S can be replaced by A can be replaced by B, and B can be replaced by A. Look at this one. B can be replaced by A. S is a non-terminal, so we will not do that. So now it means that S can give you this A. So it means that when you have this production rule, this gives you this production rule. S can be replaced by A indirectly. So we add this one when you delete this. Okay. Now look at this one. We still have another step. S can be replaced by A can be replaced by B can be replaced by S. But if you notice that S can be replaced by then again A or BB. S can be replaced by BB. So you already have that production rule BB in our grammar, so we do not need to do that because now we are in a cycle. Whenever you encounter the non-terminal from where you start, you need to stop this thing. So you don't need to go to this step because you start from S and you encounter S again. It means now you finish one circle and now you finish one iteration and now this is a second loop iteration is going on and it will give you the same thing again and again and again. So now you are in cycle. So you stop this process. Okay, very good. So now we check this one production rule. So now we check the second one. A can be replaced by B and B can be replaced by small a. So it means this will give you A can be replaced by A. Yes. So now we are saying, okay, if you have this production rule, this will give you this new production rule. A can be replaced by A if you delete this. Now we will see what happen if you do this indirectly. So A can be replaced by B, B can be replaced by S, and S can be replaced by BB. Because if you write capital A, it does not make sense. Yeah? So BB is a word, so we write that one. So now what does it mean? That this production rule will give you A can be replaced by BB. So look at this one. So we are saying that if you have this one, we will get this new production rule. A can be replaced by BB indirectly. So we check all possible things but still you can go for the next step. Let's say, so A can be replaced by B, B can be replaced by S, S can be replaced by A. And you see that you have A here, you have A here, you repeat the non-terminal. This indicates we should stop our process. We should not continue, okay? So we stop this process here. So now we pick another production rule. B can be replaced by S and S can be replaced by BB. It means B can be replaced by BB. So look at this one. And now we will see what else we can do. B can be replaced by S. S can be replaced by A. A can be replaced by small b. It means B can be replaced by small b. Look at this. We can continue this. B can be replaced by S. S can be replaced by A. A can be replaced by B. But you see that we have the same non-terminal from where we start. So this will give us a loop. We stop this process here. Okay. So now what we see, we have the unit productions, and we see that in presence of this unit production, what are the possibilities you can generate the word. We write all those production rules and all those words. Now we will delete these production rules, 3 production rules from our grammar, and add these production rules in appropriate places in absence of that production rule, and this will not give us any deficiency in the grammar. Whatever is possible in presence of those unit productions is also possible now after adding these additional production rules in absence of those unit productions. Now look at this one. So we write all these things as it is. S can be replaced by BB. BB is here, and this will be deleted. And look at this one. So these 2 production rules are S. So we write B and A here. So this will be deleted. A can be replaced by B from here. And then look at this one. A and BB. A and BB. So we delete this. B can be replaced by A. Look at this one. And then BB and B. So BB and B. And we have a new grammar. Look at this. This grammar is composed of some words. You have no unit production here. This is not unit production. It is a terminal. When you have non-terminal, that is unit production. This is not unit production. You have no unit production here. You have no lambda production here. And this is a clean grammar. And this grammar is a new context-free grammar. It is equivalent to this grammar without any deficiency. And we just kill the unit productions and we get this thing. Make sense? Okay, what is the question? If S, A, B all generate the same things, do we still need A and B? If S, A, and B all generate the same things, yes, we need that because what I understand with your question that if S generate, oh, if S generate A and A generate A and B generate A. So this I'm not sure if you are asking something like this. So yes, we need to take care of these things because how this A means if you have S, it can replace this S with A. If you have capital A, it can replace this with A. If you have capital B, it can. So these are the 3 different non-terminals which can replace, luckily, same letter, but these are 3 different non-terminals. So you can take care of all these three non-terminals. I'm not sure if I answer your question. Riley, is this answer of your question? Okay. Okay. Yeah, that's good. That's good. Any other question, guys? No question? Okay. So, I mean, if you don't have any question right now, might be you can come to office hours or send me an email so I can answer your question. Okay. Okay. So if you are happy with this, let's move to the next step. So now here it says that still there is another scenario. So we are saying if L is a language, generated by some context-free grammar. Then there is another context-free grammar that generates all the non-lambda words of language, all of whose productions are of one of the two basic forms. Uh, we do not like this thing. So now this is a unit production when you have X can be replaced by Y. This is a unit production. Or A can be replaced by B. This is a unit production. But what you call something like this, X can be replaced by AY. We do not like this also because this is also kind of unit production. It has one non-terminal there, but problem is this, it has a terminal also with that. So, but we do not like this kind of scenario also. Okay. So we what we want only, we are happy if you have two capital Y, two non-terminals, or one terminal, but we do not like one non-terminal in any case in our word. We do not like that. So this is something we want to get rid of this one. This also falls into the unit production. Okay. So it says that we want your language either non-terminal and string of only non-terminals, might be two, might be three, might be four. We have no problem with that, but just non-terminals, that's it. Not one, not one, must be more than one, or exactly one terminal. Okay, this is what we want to do. So now what we are saying, that how we do that. So we have, let's give you one scenario here, that what is the problem with that. So now we have this grammar here. So this grammar has this production rule. We do not like this. Other two production rules are good, just terminal, terminal, but this has one non-terminal and we want to get rid of that. So what we want to do, how we get rid of that? So we can either delete this, one option, or we can keep this or convert this A also into capital A or some other non-terminal. So then you will not have, because we do not want to see this. This is okay, this is okay, but one non-terminal, we don't want to see this. Okay, so we want to get rid of this. Either we delete this or we convert other terminal also into non-terminal. So this is basically what we want to do. So now we have this thing. So now look at this one. What does it mean? It means S is equal to NA, N is equal to A, N is equal to B. This is N can be replaced by B. So this means this. It is, we write this in a short way. So now we have this N and sorry, this A, and this A can be replaced by N. One can think this way, that is it okay if we replace this A with N, because we know that if we replace this with N, then N can be replaced by A, later we can replace this by A. Yes, but this has a problem. What is the problem? When if you do this, let's say if I replace this N with A with N because of this production rule, and then I have this grammar, and now I'm asking you, can you please generate a word BB? You can generate this word from here. S can be replaced by NN, NN can be replaced by B. This first N can be replaced by B, second N can be replaced by B. You can generate that. Yes, it is not impossible. But look at this one, the original grammar. If you have this original grammar here, are you able to generate this word BB? S can be replaced by NA, N can be replaced by A or B. So you can only able to generate BA. You will never able to generate only one word BB by this grammar. So it means that this way of conversion is not good, that you can use existing production rule and replace that terminal with a non-terminal. So this is not good. This is not good. Okay. So whenever you have a non-terminal, you have a terminal which is written beside a non-terminal, so then this terminal is different from existing another production rule which represents the same terminal. So consider this A as a separate A, this A as a separate A. Okay, so consider this is a separate. So now to replace this, you need to add a new production rule. So you are saying, okay, okay, let me write this. I have this production rule here, N can be replaced by A or B. To replace this A, I add another production rule. A can be replaced by A, and now I can replace this N with capital A. And this A will give me guarantee that this A, whenever I want to replace, you will never put B there. You will always use this production rule, and which will be A, and there is no discrepancy now. Okay, so that is a scenario that you can add whenever you want to replace any terminal which is beside non-terminal. So do not use existing production rule of that. Add a new production rule with a different non-terminal and then replace that with that one. Okay, this is another scenario of that. I hope you understand this thing. Anyone has any question? No question. Okay. So if you understand this thing, so let's go to the next step. So next step is that we are saying if you have a grammar and this grammar is a context-free grammar, we can convert this grammar into Chomsky normal form, CNF. You can convert your CFG into CNF. And how you know that you convert this? If all production rules of your Chomsky normal form are in this format. Exactly two non-terminals and exactly one terminal. Job is done. If your grammar is in this format, that you have a non-terminal and it has exactly two non-terminal, or you have non-terminal and exactly one terminal. I put T here. One terminal. It means this grammar is in Chomsky normal form. And this will be as context-free grammar, but this is the purified form of context-free grammar that it is in a Chomsky normal form. So when you have a Chomsky normal form, what does it mean? You do not have a lambda production there, you do not have a unit production there, and all the production rules like this kind of scenario which I just discussed you here. So this kind of scenario, combination of terminal and non-terminal, you do not have any production like that. It has very nice, neat, clean, just two non-terminals or exactly one terminal. That's it. All production rules are like that. Let me show you how it look like, and then we will see how we can get this. It will look like something like this. Look at this one. Two non-terminal, two non-terminal, non-terminal, two non-terminal, two non-terminal, exactly one terminal, two non-terminals, two non-terminal, one terminal, 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 two non-terminal, two non-terminal. This is your CNF, Chomsky normal form. How we get this? That is a separate question. First of all, do you understand what is Chomsky normal form? How we get that? We will see just now. But what is Chomsky normal form? If all your production rule are in this format. So now we are saying that if you have a language and this language can be generated by a context-free grammar, and this context-free grammar has a lambda production, has a unit production, has all possible problems, there must be another grammar which is a Chomsky normal form must exist for that context-free grammar which will be in Chomsky normal form. What does it mean? It has no lambda productions, it has no unit productions, all production rules are exactly in this format, that one non-terminal have two non-terminals, one non-terminal have one terminal. Okay, this is some cases when it is really impossible to work properly, we add uh, sometimes lambda also in that, but very rare cases. So okay, so we will see sometimes there in the future. But here now it in Chomsky normal form. So far, we should not say that. It should not have any lambda productions, and all production rules are in this format. So how we deal with this? So let's say we have this grammar. If you see that this grammar does not have any, we are talking about this grammar. So this grammar does not have any lambda productions. It does not have any unit productions. It do have these kind of production rules which we don't like. And I told you that you need to either convert all these uh, thing either into capital or you delete that. So we will follow this method. This method we add additional production rules and we can replace this small a with a capital A. So we can do that. So then we will see what if it has a lambda production. So your first step will be kill lambda production. If it has a unit production, the second check will be kill unit production. Third step, take care of all these things. Just convert them all capital, and you will be follow the next step. So now to do that, you see that we have this A can be replaced by A, B can be replaced by B. But these two A and B are different than this A and then this B, this B, this A, this B, this A. They are different and this is different because they are with terminal non-terminals and these are alone. So it will create a mess if you replace this B with capital B. This will be a mess because you saw that what is the mess there in the previous slide. It will be there. So we add additional production rules. So what we will do, we add A can be, so this is good. A can be replaced by A. This is good. Where it is. A can be replaced by A. B can be replaced by B. This is good. B can be replaced by B. We are happy with this one. We write these as it is. But now we need to convert these A and B's into non-terminals. We add two extra production rules. X can be replaced by A, Y can be replaced by B. We add these two production rules. Wherever you see, and this A and B are different than this A and B. Okay. So now, first production rule, S can be replaced by BA, B can be replaced by Y. So we write YA here. Okay. And then A can be replaced by X, XB here. Look at this one. Y, so we write both of this. B, it is YAA. XS. ABB. So look at this one. XBB. BS. YS. So wherever you have that terminal, the new production rules, you add that, use its non-terminal and replace that. So then you can, so then we done the first iteration that our all production rules are either combination of just non-terminals or just terminals. But still, this is not Chomsky normal form because Chomsky normal form says exactly two non-terminals, whereas you have three non-terminals here. So now we need to convert that into two. So what we will do, we will start looking from right to the left. Do not see from left to right. Always start. So like this one. A, Y, A. We look from right to left. We pick these two and assign them to any new production rule. So we are saying that we have a new production rule R1. R1 is any non-terminal. So we do not want to exhaust all possible English alphabet letters. So sometimes we pick one letter and reuse that with the different numbers R1, R2, R3. These are because different number. This will tell us that this is not R1, this is R2, this is different non-terminal. So this way we will not be confused by so many English alphabets. So it is easy for us to figure out that which non-terminal is used for what purpose. So we can also do this also. So we are saying we have this AA and this AA can be replaced by R1. And now if this AA can be replaced by R1, so then what this production rule will be look like YR1. Yes. So we are saying add this production rule and replace this 2A by R1. So these two and delete this. So now if you see this, we delete this production rule in our grammar. add these two production rules in place of this production rule. So the same is the case with XBB. So we consider BB as R2 and XBB will become XR2 and we delete this production rule and we add this one. And now look at this final result will look like what? So final result is so this one SYA SXB is there, YAXB this is there. Then AYAA can be replaced by these two production rules. So we delete that AYR1, R1AA. Look at this one, YR1 and what? And then R1AA, R1AA, we add that. And so we delete this. And XS and A, it is already there. S, X, S, and A. So we have this thing, okay? And then we have this thing, we replace that with these two production rules. So we add this one XR2 and R2BB and then YS and B and then XA and YB and job is done. So now we have a new grammar which has exactly all the production rules are in this format. Exactly two non-terminal or exactly one terminal. And what is this? This is your Chomsky normal form. Okay. So I hope that you guys, okay, I can write this here, that these are in this format, either two non-terminal or just one terminal. Any question here, guys? So what mistake you will do? Let's say I have A, Y, A. Do not start making two pair of this and two pair of this. This is not good. Always start reading from right to left. First replace these if you have four. So these two by something and then whatever the new thing. So then replace these two by that one and then three, they again two by another one and then again two by another one. So this is, I mean, always start from the right side and do not make pair of two, like divide this into two pairs. No. So it will be different. Okay. So now you have this Chomsky normal form, and now I think the major part we covered. It's just some few definitions and very few slides left, and then we will finish this chapter. So it says that in a sequence of terminals and non-terminals in a derivation called a working string, if there is at least one non-terminal, the first one scanning from the left to right is called the leftmost non-terminal. Okay, so you saw that before in previous chapter that when you have some word like when you try to derive some word, you start from the start production rule, let's say, and then replace s with something what is given here like this way, and then something like this, and then you have no idea that in the next step either I should replace this non-terminal or I should replace this non-terminal. So now we are saying no, machine will be confused. You are intelligent, you can see, and you have a final word in front of you, and you can make a decision that I should replace either this one or this one, but machine cannot make this decision for you. So machine says we need a deterministic approach, only one way of doing this. So what we are saying, whenever you have more than one non-terminal in your word, please start scanning from the left side. And whenever you encounter the first non-terminal, replace that with its respective production rule. And then again, start scanning from the left side. Whenever you encounter the first non-terminal, replace that. This is called leftmost non-terminal. So this is called leftmost derivation. This method is called leftmost derivation. That you have more than one non-terminal, you always start scanning from the left side and always replace the first non-terminal. And this way, will be consistent and machine can make a decision very easily. This is called leftmost derivation. When you always replace leftmost non-terminal. So this method is called leftmost derivation. So look at this one. We have this grammar here. We want to generate this word A B, sorry, A. This is, we have this word in front of us. Target is always be there. So you are saying, okay, I am forced to use the start production rule because this is a rule here. I replace this A as X. So now I can replace S also. I can replace X also. But this is leftmost derivation. So we start looking from the left side and the first non-terminal is S. I replace that. I replace that with AS again. ASX again. Look at ASX. Okay. So look at this one. So now I replace that with ASX, and then again I scan this. I find this is a non-terminal. I replace that with B, and then I scan this. I find this is a non-terminal. I replace that with XB. I scan this. I find this is a non-terminal. I replace that with A, and then I have X. I replace that with A, and finally I achieve my word. But if you see here now, it is easy for a machine to do that because machine is not picking any non-terminal anywhere from your word. It is consistent. It always scan your words from the left side and pick the first non-terminal it encounter on the left side. This is called leftmost derivation. Okay. If you have this tree here, you want to derive this word. Let's say A, B, B, B. Look at this one. And you see that if you there are multiple ways to derive this thing. So you can have, so if you, so this is ambiguous grammar. So you have two ways to derive this. So you have this tree and this tree. You can derive either by this way. S can be replaced by XX. That's X can be replaced by XX. And so instead of this, you replace this X with XX. Here you replace this X with XS. This is a difference here. And but you get the final word. So this is inconsistent. Okay. But now if you want to do, so machine will confuse that two derivation tree, ambiguous grammar, what I can do. So now in this case, if you follow leftmost derivation rule, regardless your grammar is ambiguous, your machine will always be consistent. So now what happened? Something which is non-deterministic, by applying a rule, we make it deterministic. So this is ambiguous grammar is non-deterministic, but this restriction, always follow the leftmost derivation. You behave in a deterministic way. So this will be not create any ambiguity here. Look at this one. So you always replace your leftmost non-terminal. Look at this one. Dot says that this is current non-terminal. You will replace this X, replace this X this way. So you will achieve your target word. So you have this way. You can replace this X always this one. So where any non-terminal which has dot on top, it shows that this is the leftmost non-terminal, and you are replacing this in the next step. So you see that we follow the leftmost non-derivation method, and we can achieve the target word by both means. So this will not be create any confusion, and you can easily follow, you can generate or derive a word, whatever word is possible by that machine, if it is acceptable by that, by using the leftmost derivation. Leftmost derivation will not create any confusion um, or any problem. It will able to do all those jobs. It will able to perform all those jobs which you can do without that. Okay, so it is, but this is more deterministic, more consistent for the machine. So look at this one. So we have, it was nightmare at that time how to draw this thing at that time. So now we have this grammar, and you follow the leftmost derivation. So S this S. So you always follow this to the first non-terminal, and you can derive your desired word by the derivation method. Okay. So it is very easy now if you have. So the thing is that you write a code for this and create a machine which can write this code. You can write this code, and it can always follow the leftmost derivation and use the suitable production rule and apply that. So this is basically what we are saying here. And we are done. We finished this chapter. And any question, guys? This is very important chapter. Any questions? No question. Okay, so then let me stop this recording here.